Okay, good evening. Okay, we'll start now. Okay, we have a lot to cover. Okay, today we will do recursion. It's in lecture week 7. So we skipped this previously. Now, recursion is an integral part of programming. You will not be able to avoid recursion, okay, once you do program long enough. And in almost every single programming language, you have this recursion, okay? So you can ignore this. I don't know what nonsense they're talking here. Now, basically, recursion is a function that calling itself. That is recursion, okay? So normally we create a function, then from the main program or from some other routines, you will call that function. But in this case, the function is calling itself. For example, this is a function to return a factorial. But notice that inside this factorial, there's a factorial as well. Okay. So when you see a function name inside its own function, that is recursion. Clear? Okay. Now in these notes, you will see two examples of recursion. One is factorial, the other one is Fibonacci sequence. I think factorial you know already, right? Zero factorial is 1. That is a base case or exceptional case. But after that, n factorial is n times n minus 1 factorial. Okay, so this is the formula for factorial. Remember, factorial 4 is basically 4 times 3 times 2 times 1. Factorial 3 is 3 times 2 times 1. Factorial 2 is 2 times 1. Clear? So 4 factorial is basically same, right? Okay, 3 times 2 times 1, 3 times 2 times 1 is also 3 factorial. So basically 4 factorial is 4 times 3 factorial. Clear? 3 factorial is this 2 times 1, which is 2 factorial. So I can say n factorial is n times n minus 1 factorial. Clear? Okay. So this is the formula. N factorial is n times n minus 1 factorial. So the question is, how do we program this? Now this is a factorial function. So this is high factorial, which is iterative factorial. This is the normal way that we program. So basically using a for loop from 1 to n, okay, we times k times factorial. This factorial means previous factorial value. So if the previous factorial value is 3 factorial, then this is 4 times 3 factorial. Once you go to 5, this is 5 times 4 factorial. Clear? So this is iterative, which looks nothing like the original formula. Now this is the original formula. But if I change this to recursion, this is the result. So this is the base case. If n lesser or equal to 1, return 1. else, return. Notice your n, which is this, n, times r factorial, which is this, which is the factorial, n minus 1. So this is exactly similar to the original formula. Clear? So if I use recursion, I can copy, I can mimic, I can duplicate the actual formula. So I don't need to prove mathematically. I know that it will work. Clear? Okay? So this is one reason why we use factorial. Because it simplifies a lot of stuff. And in this case, it resembles the original formula. Clear? But how does it work? So let's say you call this r factorial. Okay, so you call this r factorial. Let's say we pass number 4. Okay, so n equal to 4. So it will check if n lesser or equal to 1, return 1. But definitely n is not 1 because n is 4. So it will go to this else and then it will return n, which is 4 times r factorial n minus 1. So notice that this is similar to this. So what happened is, internally, you spawn or you create another r factorial. Now we are talking about in memory. Okay, in memory. So another r factorial will be created. But this time around, it will pass this value. 4 minus 1, so 3. So 3 will be passed here. And then it will check. This is definitely not 1. So it will go to else. So it will return 3 times r factorial 3 minus 1. Now 3 minus 1 is 2. So now you spawn another r factorial. So another one will be created. So this is passed to n, this value. It is not 1, so it will go to else. So this is 2 times r factorial 2 minus 1, 1. So this will spawn another r factorial. So now this is 1 is passed. Now all these are still open. So actually it will take more memory space. So now n is lesser or equal to 1. Clear? So now this is true. So once this is true, it will return. So finally it will return. So it will return number 1. So this whole thing will close. And then it will return 1. So meaning this will be replaced with 1. Clear? So now this is completed. So return 2 times 1. 2 times 1 is 1. So this will be closed. 2 times 1 is 2. So it will return number 2. So this becomes 2. So this one is completed. 3 times 2, 6. So this will close and it will return 6. So 6 times 4. So you will get, this will close, it will return 24. So 4 factorial is 24. So that is what happened inside your computer. Clear? So when you do recursion, so notice that there is no for loop here. If I use for loop, what is the complexity of this? 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 What is the complexity of this statement? What is the complexity of this statement? N. Okay, N. Now there is no looping here. But from this diagram, you can see that if I have 4, then I'm going to execute like 4 times. If I have 6, about 6 times, and so on. So this is same as your for loop. This is still N. Clear? Okay. So in recursion, if I have to call once, okay, if I have to call once, that is N. So in this case, the complexity of this is N. Clear? Now you need to make sure that when you create a recursive function, it will stop. You can imagine what will happen if it doesn't stop. You're creating this in memory space. Open, you open. If there's no ending, sooner or later, you will fill up the RAM. Then basically your computer will freeze. Clear? So it must stop. So that's why you have base case. So in recursion, you have a base case so that it will stop. Now in this case, I know that it will stop eventually because I have this base case. If n lesser than 1, return 1. So it will not forever opening another recursive function. Okay. And whenever it opens another recursive function, notice that it says here n minus 1. So meaning I know that my n value eventually will become 1. Even though you put 1 billion, eventually it will become 1. Because every time you open, you minus 1, minus 1, minus 1, minus 1. Clear? So you cannot simply create recursive. You need to make sure you understand this. Okay? It has to eventually meet its base case so that eventually it will stop no matter what. Otherwise, it will take your entire memory. Okay? Clear? So in terms of speed, you can see that there is not there's no different. Okay? In terms of memory, this definitely better because this is a normal looping. You are not creating any additional extra RAM. But in terms of code elegance, in terms of its accuracy or its resemblance to the original formula, definitely recursion better. Clear? Okay. Now another example is Fibonacci sequence. Now in Fibonacci sequence, if you take one number, for example number 5, the result is the sum of 2 previous Fibonacci. Okay, meaning Fibonacci 5 is the result of Fibonacci 4 plus Fibonacci 3. Fibonacci 1055 is the addition of 3 and 34 and 21. Clear? Except for 0, because 0 has no 2 previous, so 0 is 0. 1 also have no 2 previous, so 1 is 1. So actually the calculation starts from 2, because 2, 1 plus 0 is 1. Clear? This is Fibonacci sequence. Okay, don't ask me what it is used for. I think previously it's used for some animal reproduction, those kind of things. Okay, they want to know the numbers. Now, if you see the formula, this is basically Fibonacci n is Fibonacci n minus 1 plus Fibonacci n minus 2. So that's the formula. Okay. Now, if I write this in iterative method, So this is what I will get. Okay. So if it is lesser than or equal to 1, I return n. If 0, you return 0. If 1, you return 1. And then you need to keep track of the previous two results. So I have A and B. A will keep track the second last result, and 1 is the last result, the immediate last result, B. And then you will do the normal looping starting from 2, because 2 is when you actually calculate. Okay. And then you add the previous and the previous. Now once you have added, so the previous become the current become previous, the previous become previous. Clear? Then you start again. Okay, normal looping. So at the end you return B, which is the result of this. Okay. So you can see if I use iterative, it is a bit messy. Okay, it's a bit messy. It works, but it's a bit messy. The complexity of this, you can see it goes up to n. So on. Okay. But if I use recursive method instead, so this is a formula: Fibonacci n equal to Fibonacci n minus 1 plus Fibonacci n minus 2. So this is exactly, okay, how the formula is represented. So if n less or equal to 1, you return n, else you return Fibonacci n minus 1 plus Fibonacci n minus 2. Clear? So instead of this long-winded algorithm, I can simplify this, and this look exactly similar to original formula. So as mathematician, for example, definitely they love this better, okay, compared to this. This is a programmer way. Clear? So what actually happened, okay, when you do this recursion? So let's take, for example, one Fibonacci call. So let's say, for example, we want to know what is Fibonacci 3. Okay. Here it says Fibonacci 3 is 2. So Fibonacci 3 is definitely not less or equal to 1. So it will do this, else return Fibonacci n minus 1 and Fibonacci n minus 2. So notice that there are 2, not 1. Okay, 2. So actually you will spawn 2 Fibonacci. One for this, and then the other one is for that one. So this is 3 minus 1, which is 2. This is 3 minus 2, which is 1. So this is 1, this is 2. Now 2 is not less or equal to 1, so you will do this else. So this is 2 minus 1, which is 1, and this is 2 minus 2, which is 0. So here you are going to spawn 2 more. So notice what happened. Every time you call, you are creating 2. Okay? You are creating 2 Fibonacci, not 1, but 2. So this one is 1. So 1 minus 1 is... so now this one is 1. So this it satisfies this condition. So you will return n. So you will return 1. So this one will be closed. And then it will return 1. So this whole thing is 1. Okay. So this one is 1 and this one is 0. Now, so this satisfies this condition, so it will return 1. So this will close, it will return 1. This one will close as well because this is 0, it will return 0. So this one will return 0. So 1 plus 0 is 1, so this will close and it will return 1. So 1 plus 1 is 2, so the entire thing will return 2. Clear? Okay? But what you should be aware of is every single call will create 2 Fibonacci. Now this is example of n square. Okay? Because what you are creating is this. Double, 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 double. So if there are 3, then it becomes n cubed. So even though this Fibonacci is very short, what we call an elegant solution, but actually internally, okay, it can take a lot of memory space. And in terms of complexity, this is worse because this is exponential, okay, compared to this. So you have to be very careful, okay. So we don't use recursion mainly for speed. Most of the time use recursion either because the solution is simpler, easy to troubleshoot, easier for people to understand, or there is no choice. Okay. In certain cases, if you don't use recursion, the equivalent iterative are very messy. In certain cases, you have no choice. The only solution that it will work is by using recursion. Okay, clear? So as much as possible, we try to avoid recursion, but in certain cases, it's unavoidable, and in certain cases, you have to use recursion. But make sure you're aware of its complexity and the reason of why you are using this on the first place. Clear? Any question? Any question? Clear? Okay. Okay, so make sure you know how to create the Fibonacci iterative and recursion. Okay. Same with the factorial, iterative and recursion. So starting from this point onward, you will see many algorithm that you have to solve using recursion. Okay, if you have started your sorting or your searching, you will see this recursion algorithm. Okay, so in certain cases it's unavoidable. That's the way to solve that problem using recursion. Any question? 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 Okay, next. Okay, now we will go into searching. You have learned sorting. So sorting is sorting. Sorting is to arrange. Now is searching. Okay. Week 9 tutorial. So the first type of sorting is binary search. Actually, before binary search, there is more primitive searching. Linear search. What is linear search? Linear search is the way that we search like normal human. Okay, so basically you just go from the first until the last and try to find whatever that you're searching for. Okay, that's linear search. Okay, But the problem with linear search is it depends on your luck. If you're lucky, whatever you search is in front. If you're unlucky, whatever you search is way at the back. So it will take a long time. Okay? So linear search really depends on your luck. Definitely when you use computing, we don't want to depend on our luck. Okay? So we improve. So one way is to use binary search. Okay? But notice this number are all sorted. So one of the requirement, if I want to use binary search, the list must be sorted. Clear? Okay? So that's why you need to learn sorting first, then searching. So how does it work? Now in binary search, because the list is sorted, so let's say you're searching for number 33. So you don't go for the first, you don't go to the last, you go exactly to the middle. Okay? So you go exactly to the middle. In this case, the middle is 53. Now remember, this is sorted. So once I see the number is 53, immediately I know that it is impossible for 33 to be on the right side. Clear? Clear? So just by one comparison, I've omitted half of the list. 50% gone. Okay? So instead of this is low, this is high. Now I will change this mid to high. So now my searching will be this range only. Okay? So in my second step, I only search for that part. Okay, which is this part. So this is my new low and high. And again, I will go to the middle. I don't care where that 33 is, I will go to the middle. And again, because this is sorted, it means your 33 will be somewhere to the right. Impossible to be on the left. Okay? So now I will remove this. So after first search, half gone. After second search, a quarter gone. So only after 2 searching, you have reduced your list to only 1/4. Clear? So now this is my search area. So again, you go to the middle. And because it is sorted, you know that it will be on the left side. So now you're on the left side, you go to the middle, and that middle is the same with whatever you're searching for, then you stop. So in this case, only after 1, 2, 3, 4 comparison, I already get my number. Okay? In fact, it will not be any more than 4 comparison. Because I have 14, so if I put log to 14, what is the result? It's lesser than 4, right? Okay? So it cannot be more than 4 steps. Clear? Okay? So that's binary search. So given a list, you cut into half, next you cut into half, until you get whatever you're searching for. So you can see this is very fast, very quick. Okay? Clear? So this is one of the fastest way to search. Binary search. It's called binary because binary is 2. So basically you cut into 2, cut into 2, cut into 2 until you find whatever you are searching for. Clear? So the complexity of this is log n. Okay? So it's log 2n. So O log n. And log n is what we want. Okay, what we want. We want our algorithm to be logarithmic. Okay? So it's the best case scenario is logarithmic. Now this is the code for binary search, okay, which I've copied here. So what we will do is we will compare linear search. Remember, linear search is basically just a dumb search. You go from the first until the last, okay, and hopefully you find whatever you're searching for. That's linear search. So in linear search, you go from the first until last, okay, and in this case we count how many steps that we need to do in order to get whatever you're searching for. So key is whatever you're searching for. So once I've gotten the match, then I will break, okay, meaning I will stop, and then I will return index. Index is the position. Remember, you're not interested in the value, because the value, you know what is the value, is the one that you're searching for. You're interested in the position, where actually this thing is positioned, okay. So this is linear search. Now notice also I need to have bubble sort, because I need to sort. You can use any type of sorting, okay. In this case I use bubble sort because this is the simplest type of sorting and it's quite short. Now this is binary search. So this is the code for binary search. So notice that you have the list, and then you have the first and the last. The key is what you're searching for. So this is the one that decide the range, okay, the range that you're searching for. So when you first start, the first and the last is the first and the last of the list. So index -1, meaning if you get -1, something is not right, okay, because you cannot find the key that you're searching for. Now if index greater than last, meaning something is not right, okay, so you give -1. Otherwise we go to the middle, okay, so we get the middle first, divide by 2. Now we count the steps similar to our linear search. Every time we make a comparison, we count the step. Okay, this is the comparison. So every time you compare, you count the step. So in this case, this is the comparison. So every time we compare, we count how many steps needed. So if whatever you're searching for is similar to the middle, then you can stop, okay? Else, otherwise, now you need to go into either the left side or the right side, okay? Half. So if the key is lesser than the middle, meaning what you're searching for is smaller than the middle, then you know that you need to go to the left. If I go to the left, I start from the beginning, and then my right will be the middle. If I go to the left, my starting is the middle, and my last is the last, okay? And notice that this is binary search and this is also binary search. This is an example of recursion, okay? So it's calling itself. Now there are two binary search here, but unlike your Fibonacci, you are not executing both at once, okay? In Fibonacci, you are executing both at once. This one is either left or right. Clear? Okay? So it's either left or right. Okay, and then you return the index. Okay? So first we put a random number. Okay, random number inside the list. We limit to 100 because we want to be able to search for the value. Okay, so the number is from 0 to 999. Hopefully there is no duplicates, because duplicate can mess our searching. Okay, then we display the list, and then we ask the user to enter the search value. The user need to be able to see the list first. then they can search whatever value, and then we perform linear search, and then we see how many steps taken. Then we do the sorting, and then we perform the binary search, and then we see how many steps it takes. Okay. So let's run this. So this is my list, and these are the contents. Now first I need to enter the search value. Now let's say, for example, I search for 558. Worst case scenario for linear search, 558. 558, there is a duplicate here, but it's okay. So it says here, for linear search, you need to take 81 steps, okay, to get to this 558. But for binary search, you only need to take 5 steps, okay. So it is a lot faster. Now let's say if I run again. So let's say I take something in the middle, which is better for linear search. 504. So linear search, position 45, somewhere in the middle. But binary search only need 4 steps. Okay. So again, very fast, very quick. Now let's say if I run again, I take something that is nearer to the beginning. So to give favor to linear search, let's say if I take 337, okay, 337. So at position 7, but your binary search take only 6 steps. So it's clear that binary search is a lot faster than linear search. In fact, if we see log to 100, meaning it cannot be more than 7. Okay. So because of this, instead of using linear search, most of the time we prefer binary search. Clear? But there's a problem with binary search. What is the problem? Anyone? It's faster than linear search, but that is not the entire story. What is the problem with binary search? What do you mean? You mean if you take 7 for 1? That one definitely. Okay, 1 and 7. Okay, but that's only for this. How about for the rest? So I'm willing to sacrifice for the first few, so that after that I will get a faster result. What is the problem with binary search? Anyone? Anyone? So in this case, given a choice, linear search and binary search, I may go for linear search rather than binary search, depending on the situation. So what is the problem with binary search? What's the problem? What's the problem? What's the problem with binary search? Okay, so specifically, what is the problem? think about your running time. Think about this code. If you want to use binary search, what do you need to do first? You need to sort. Clear. So let's say, for example, if I take this, so your linear search is ON. Okay, is for loop ON. Your binary search is better, is O log to N. Clear. So definitely binary search is faster. But if I want to perform binary search, what do I need to do first? You need to sort. And what is the complexity of the sorting? Let's say if you take bubble sort. What is the complexity of bubble sort? O N square. So when I add these two, what is the big O for this? What is the big O for this? So what is the complexity of the entire thing? O N square. So now which one is better? So you see the problem? Okay. If I only need to sort this once, let's say for example you are sorting the list of names of past American president. So it never change. So you only need to sort once. Then it's fine. Okay. I only sacrifice once and then I can get a lot of searching. But if this is the list of current Taylor student, so you can imagine every time there's a new student, you need to resort. Every time you have a new student, you need to resort. So what is the benefit of the binary search? When actually you have to suffer from this. Clear? Okay. So this is the problem of binary search. Okay, because you need to sort, and at best, when you sort, even though you do the fastest type of sorting, it's still O N. Okay. So what is the solution? What is the solution to this? We have to fix the sorting part. The searching part is fine already. So we need to fix the sorting part. And there is one type of binary search which can sort in log to n and search in log to n, which is called binary tree search. Clear? So instead of using normal search, normal binary search, which requires sorting, which normally take O n square, if I use binary tree search, then I have solved the problem. Because the sorting is log to n and the searching is also log to n. Clear? So we will go into this binary tree search in your next tutorial. Okay? Any question? Any question? 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 Okay, okay, at this moment I will try to have our feedback for midterm next Tuesday. Okay, hopefully we can do next Tuesday. But I will release your mark this week. Okay, either Thursday or Friday, it depends, because I have to key in one by one. It's 400 plus of you. Your result will be inside It will be here inside these grades. So you will see this here. Okay, clear. So once the result is posted, then I will message in the group so you can see your result here. Okay, so don't ask me where to find the result. It's in your times. In fact, all the result will appear here. Okay. Any question? Any question? Clear? Now you have your group assignment, you have your subgroup assignment. Now this test 2 is not a test. This is actually part of your subgroup assignment. Okay. So there will be an individual test. But it's open book. But that will be done in your final week. Okay. Any question? Any question? 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 Not final. This one is 10%. It is part of your subgroup assignment actually, but you do individually. Question is not really open book, it's open notes. Okay, you're not allowed to bring any other thing except notes. Any question? Like this thing, but up to you how many you want to bring. Okay. Print them out. You don't need to bring all the notes, only the one that is covered by the topics. Okay. The topic is very specific. Any question? You have not learned the topic yet. Okay. So the topic is something that we cover in your final as well. So if you learn or you study for that, actually you study for your final as well. Okay. So that's why it is held at the very end. Any question? 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 Okay, your attendance. Now remember, for your video assignment, the part where you need to have live video is the mandatory part is the video demonstration only. Other than that, it's up to you. But there's only one submission, which is the video and the video only. There is no supplementary, there is no Word document, nothing. Everything is put inside that video. Clear? Okay? Minimum one person need to appear 20 seconds. Okay, minimum. You can appear for 7 minutes, 6 minutes, doesn't matter. But minimum 20 seconds. Yes. every member, minimum 20 seconds. Clear? If 2 people appear for 20 seconds, meaning that 2 people is it basically meet the requirement already. Okay. So up to your group to allocate. Any question about the assignment? For the searching part, you don't need to show how it works, okay? You only need to show the code, and you need to show the code because you need to show how you get the complexity. Without the code, how do you explain? Okay, how do you get the complexity? So you must have the code. So from the complexity, then you can show the dominant term, and from the dominant term, you can show the big O. That's all. Clear? So the big O, the dominant term are the result. How you get from the code to the result is the process. That is your complexity analysis. Okay? Clear? Any question? Now the submission link will only be open 1 week before the due date. Okay, I will not open earlier. Okay, 1 week before the due date. Okay, and you can resubmit as many times you want, because I will not mark until the due date. Clear? Any question? 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 And please comply with the time limit and the size limit. Okay? There's no compromise on that. Now, if you exceed little bit, not a problem, but not by much. Okay? Clear? Okay. You can leave.